Now we're going to take a look at the sum and difference of sine, the sum and difference of cosine, and the sum and difference of tangent. Now if we look at this first group of formulas, the cosine of a sum or difference, this first formula is written or is expressed as the sum of cosine. Right? The second formula is denoted as the difference of cosine. If we take a look at the sine formulas, this first formula is known as the sum of sine. The second formula is the difference of sine. And then we have the difference and the sum of the tangent. Okay. Now keep in mind that these formulas are used to find the exact values of the trig functions. All right, so here's what I mean by that. Okay, now as far as the way that these formulas are derived, I'm going to go back to the lecture notes section. And in section 9.2, and there's also a video for this sum and difference. There is a section 9.2 set of notes, and here is how the sum and difference formulas are derived. All right, so I won't go through this in entirety, but I kind of walk you through it. All right, so here's the setup. We have two angles. Kind of blow this up. There is an angle A. Right, so notice that all of our angles start along the positive x-axis. So here is angle A, right? So here is the rotation for angle A. And then we have an angle B, right? So this is our angle B, right? So we have an angle A and an angle B. We also have an angle A minus B. All right, so the blue angle is the angle A minus B. All right, and then we have what are called chords. And a chord goes from one rim of the circle through the other. Right, so we have R, S, Q, and P. Right, and these things are just based on the terminal side for our three angles. All right, so P is the actual where the angles start. Q has the coordinates cosine B, sine B. So here is Q. All right, so this was our angle B. So remember that the first coordinate is cosine of your angle. The second coordinate is the sine of your angle. All right, so Q has the coordinates cosine B, sine B. S has the coordinates cosine A, sine A. So here is S, right? And that was the terminal side for angle A. So it has the coordinates cosine A, sine A. We also have R. R has the coordinates, the cosine of A minus B, right? So here is R, right? It's the terminal side for the A minus B angle. So it has a cosine of A minus B and a sine of A minus B. Okay. So it says that angle SOQ, so here we have SOQ is equal to A minus B. Since SOQ and POR, so here is POR, they're equal, right? We can set the chords equal to each other. So a chord, PR, so here we have PR, right? The length of this chord and the length of chord SQ are equal. Right? In order to find the length of these chords, we use the distance formula from algebra. All right, so here's what's kind of going on. We have PR, that's equal to SQ as we just saw in the drawing. In order to find the length of PR, right, if I go back to PR, which is here, right, we can use that distance formula. Remember from algebra, the distance formula was the square root of x sub 2 minus x sub 1 plus y sub 2 minus y sub 1. And that's what we have here. But instead of using x sub 1 and x sub 2 and y sub 1 and y sub 2, they're actually using the cosine values. Right? So the PR, its distance is here. That's equal to SQ, its distance is here. Once the square root is removed and it's solved for the cosine of A minus B, out pops the identity, right? This says that the difference of cosine, right, the cosine of A minus B, that's equal to the cosine of A times the cosine of B plus the sine of A times the sine of B. Right. And from this formula, we can derive the other sum and difference formulas. Right. So I'm going to kind of bypass on how these things are derived, and we're simply going to concentrate on the formulas and how to use them. All right, so when would you ever use formulas such as these? All right, I'm going to go into the next section. Section 3.2, and we're going to take a look at the very first problem, right? We're asked to find the exact value. And in this instance, we're given the cosine of 1/12 pi. All right, so first I'm going to figure out what pi over 12 is as an angle measure, or as a degree measure. So remember that pi is 180, and I'm going to divide that by 12, right? And we have 15 degrees, so we want the exact value for 15 degrees. Now, normally when we're finding exact values, we will use the unit circle. All right, so give me 1 second. I'm going to bring up the unit circle. All right. And lo and behold, we do not have a 15-degree angle measure. All right, so what do we do from this point? Well, if I were to put the cosine of 15 degrees in the calculator, just make sure that I'm in degree mode. All right, notice it's not giving me an exact value. It's giving me an approximated value. So here's where the sum and difference formulas come in. Now, even though I don't have a 15-degree angle, I can take two angles and subtract to get a 15. Right? I can take 45 minus 30, right? Because 45 minus 30 is 15. I can also subtract 60 minus 45. I can also get a 15 by using 135 minus 120. Right? And I'm bringing this up because it does not matter which angles you use, as long as, in this case, the difference is 15 degrees. Normally, you want to use angles that are in the first quadrant, right? Normally, because they're easy to work with. However, we can use the unit circle function values chart. Okay, we're going to see how this thing also kind of plays in on what we're doing. All right, so let's go back to our question. How can we find the exact value for the cosine of 15 degrees. All right. So first off, we started with the cosine of pi over 12. All right, from this point, I simply converted the radian measure to a degree measure. So we have the cosine of 15 degrees. All right, so when you're working with these sum or difference formulas, it's best to express the angle measure in degrees because the brain works best in degree measures. So now, how can I use a combination of the angle measures in the unit circle to get 15 degrees? Well, I'm going to use 45 and 30, right? So I'm going to rewrite the cosine of 15 degrees as the cosine of 45 degrees minus 30. All right. So I'm going to utilize the difference of cosine formula. Right, so right above the problem, I'm going to write the formula. So the formula says that the cosine of A minus B is equal to cosine A times cosine B plus sine A times sine B. So in this formula, we're going to substitute A for 45 degrees, and we're going to substitute B for 30 degrees. All right, so substituting those things in, we have the cosine of 45 degrees times the cosine of 30 degrees plus the sine of 45 degrees times the sine of 30 degrees. And the only thing we do from this point is we simply pull out the values for the trig functions and we add them. Okay, so if you look at your unit circle functions value sheet, all right, we can kind of quickly just pull out these values. So notice that the cosine of 45 degrees is square root of 2 over 2. The sine of 45 degrees is also square root of 2 over 2. And then we have the 30-degree angle. The cosine of 30 degrees is square root of 3 over 2. And the sine of 30 degrees is 1/2. Right, so we're going to write these values where they belong. So we have the cosine of 45 degrees is square root of 2 over 2 times the cosine of 30 degrees, which is square root of 3 over 2, plus the sine of 45 degrees is square root of 2 over 2 times the sine of 30 degrees, which is 1/2. All right, so we have two terms. This is our first term, and this is our second term. Now, keep in mind from algebra, right, the square root of 2 times the square root of 3, since we're dealing with square roots, we can multiply the radicand. So 2 times 3 is 6. So the square root of 3 times the square root of 2, that's the square root of 6. Keep in mind when you add fractions, you keep your common denominator. So I don't multiply 2 times 2 and get 4. Right? I'm going to keep the common denominator. Well, excuse me, we're multiplying, not adding. So I would multiply my denominators. 2 times 2 is 4. Plus square root of 2 times 1 is square root of 2. 2 times 2 is 4. All right, so now we're to the point where we're adding fractions. We have a common denominator, so we keep the common denominator and we combine the numerators. Now I can't actually add the square root of 6 plus the square root of 2 because I don't have like radicands. Right, so what I'm saying is we can't actually add those to get a square root of 8. So this would be our simplest form, and this would be our solution. Now I'm just going to kind of check that with what we had earlier. Right, when we put in the cosine of 15 degrees, we got 0.96. So I'm just going to evaluate this in the calculator just to verify. So we have, I'm going to use the begin set of parentheses. We have square root of 6 plus the square root of 2. I'm going to close off my square root. I'm going to close off the numerator, divided by 4. All right, and we have the exact value. So in this example, we're going to evaluate or find the exact value for the sine of negative 7 pi over 12. Okay. So now on the last class, when I kind of looked through the homework problems, I didn't see any problems that had like a negative. But now I'm kind of looking at the problems today, and in some problems you may see this negative angle deal pop up. So just remember from our negative number identities, and unfortunately the only place the negative number identities can be found are, I believe it's in the lecture notes. And I believe it was 9.2. No, I'm sorry, it was 9.1. Yeah, notice we have the negative number identities, right? So if we're trying to find, let's say, the sine of a negative angle, we can actually write that as negative times the sine of a positive angle. All right, so whenever you're encountering these negative angles and you're asked to find the exact value, you can rewrite your negative angle as a positive angle. All right, as we're going to see in this example. All right, so we want to find the sine of negative 7 pi over 12. Okay, in proceeding, I'm going to simply use the negative number identity, and I'm going to write this as a negative times the sine of a positive 7 pi over 12. In this instance, I'm going to convert 7 pi over 12 to a degree measure, all right, because our final result, it's not in radians and it's not in degree measure. Our final result is the actual exact value, right? And it's easier on the brain to think in terms of degrees, right? So I'm simply going to convert 7 pi over 12 radians to degrees, and then we'll use the unit circle. Okay, and from the unit circles, we can pull out the angle measures that we need. So in order to convert 7 pi over 12 radians to a degree measure, I'm going to multiply 7 times pi, right? And pi radians as a degree is equal to 180 degrees. I'm going to divide this by 12, and we have 105 degrees. So I'm going to rewrite this as negative times the sine of positive 105 degrees. All right, so notice that there is a negative in front of our sine function. Okay, I'm going to pull up the unit circle. Right, and if we look at the unit circle, notice that there is not a 105-degree angle, but we can use a combination of angles that would give us 105 degrees. So in this instance, I'm going to use the 60-degree angle and a 45-degree angle, right? Because 60 plus 45 is equal to 105. So I'm going to rewrite this as negative times the sine of 60 degrees plus 45 degrees. Now, when you're writing this out, it really doesn't matter which value you put first. You could put 45 degrees first. You could put 60 degrees first. That doesn't matter. The only thing that matters is that your combination gives you the desired angle measure, which in this case is 105. All right. So looking at our setup, we're going to use the sum of sine formula. All right, so referring back to our formula sheet, all right, here is the sum of sine formula. The sum of sine is equal, the sum of, well, the sine of A plus B is sine A plus sine A times cosine B plus cosine A times the sine of B. Now, in this course, you're not required to memorize the formulas. You only need to know how and when to use the formulas. All right, so we won't have to memorize, so I'm simply going to rewrite this formula right above our given problem. All right, so the sine of A plus B, that's equal to the sine of A times the cosine of B plus the cosine of A times the sine of B. Right, so in this formula, we're going to substitute A for 60 and B for 45. But remember, we still have a negative in front of our sine function. All right, so be sure to carry your negative. And now I'm just going to simply substitute in the values. So we have the sine of A, which is 60, times the cosine of B, which is 45, plus the cosine of A, which is 60, times the sine of B, which is 45 degrees. All right, from this point, we're going to pull out, and notice I'm bringing down my negative. We're going to pull out the values for the sine and cosine of 60 as well as the sine and cosine of 45 degrees. And I remember there's two ways that we can find these values. We can use the unit circle, right? And if we're using the unit circle, the x-coordinate represents cosine, the y-coordinate represents sine, or we could use I'm going to go back into formula sheets, and I'm going to pull up the unit circle function values chart. Right, or we can use this document, right? We can find the cosine and sine of both 60 and 45. Right, so looking at one or the other, we see that the sine of 60 degrees is 1/2 times the cosine of 45 degrees, which is square root of 2/2, plus the cosine of 60, which is square root of 3/2, times the sine of 45 degrees, which is square root of 2 over 2. I'm going to bring down my negative. All right, we have the first term and the second term. All right, so in the first term, we're multiplying fractions. So when we multiply fractions, we multiply the numerator and the denominator. So we have the square root of 2 over 4. And for the second term, we're going to multiply the numerators. The square root of 3 times the square root of 2 is the square root of 6 over 4. Okay, I will answer that in a second. All right, and then we're going to distribute the negatives. So we have negative square root of 2 over 4 minus square root of 6 over 4. All right, and I'm going to check the solution just by using the calculator. All right, now our initial problem was given in radian measure, so I'm going to just make sure that my calculator is in radian mode. All right, so I'm going to go into mode. All right, I'm going to change that to radian. So I'm going to put in the sine of negative 7 pi divided by 12. All right, and we can see our value is negative 0.97. And next I'm going to just put in the values that we calculated. And it re-erased on me at the end. All right. Okay, OneNote's been crashing. I don't know what's wrong with OneNote. All right, so I'm going to put in a negative square root of 2. I'm going to close off my square root, right, divided by 4 minus, so remember I did distribute that negative, minus the square root of 6 divided by 4. All right, and we have the exact value. So just remember, just to reiterate, here's the difference between an exact value and an approximated value. The calculator will give us an approximated value. Okay, the exact value, okay, since the square root of 2 is an irrational number, and an irrational number, it never stops and it never repeats. So it's impossible to write out the square root of 2 approximately because it never stops. You keep writing it forever. The exact value is encapsulated in the square root of 2. All right, so when you're answering the problems and it asks for an exact value, normally that means that there is a square root somewhere in your solution. Okay, it doesn't always mean it, but most of the time it means that there's a square root in your solution, and the only way to express that exactly is symbolically. All right, now we're going to take a look at the tangent. Right, so I believe we've taken a look at the sum and difference of cosine and sine. All right, let's see where I was. Okay, but I believe we've taken a look at the sum of cosine. We've just taken a look at the sum of sine. Now we're going to take a look at the sum and difference of tangents. Okay, now when we talk about the sum and difference of tangents, on the majority of these problems, I can say all of the problems, we're going to have to do what's called rationalize a denominator. All right, so here is the example. We're going to find the exact value for the tangent of 7 pi over 12. Okay, so based on the previous problem, that 7 pi over 12, if we were to convert that to a degree measure, we would get 105 degrees. All right, so once again, it's just 7 times 180 divided by 12. All right, so notice that's the same 105 degrees. All right, so if we look in the unit circle, notice that there is no 105 degree measure. All right, so we're going to basically do what we did with the sine function. I'm going to use 60 and I'm going to use 45 degrees, right? So I'm going to rewrite this as the tangent of 60 degrees plus 45 degrees. All right. So I'm going to look back at the sum of tangent formula. Right, and the sum of tangent formula says that the tangent of A plus B, that's tangent A plus tangent B, divided by 1 minus tangent A times tangent B. Right, so I'm going to just write that above my problem. So the tangent of A plus B, that's equal to tangent A plus tangent B divided by 1 minus tangent A times tangent B. Right, so in this formula, we're going to substitute A for 60 and B for 45. All right, so this is equal to the tangent of 60 degrees plus the tangent of 45 degrees divided by 1 minus tangent of 60 degrees times the tangent of 45 degrees. All right, so now we need to find the tangent for both 60 and 45. Right, so the quickest way to find tangent values are by using the unit circle function value sheet. All right, so if we look at 60 degrees, which is here, the tangent for 60 degrees is square root of 3. If we look at 45 degrees, the tangent is 1. All right, so I'm going to just replace those values. All right, in our problem, so we have the tangent of 60 degrees, which is the square root of 3, plus 1, divided by 1 minus, right, the tangent for 60 degrees is square root of 3. The tangent for 45 degrees is 1. If we were to multiply those two, we would have the square root of 3. All right. All right, so just remember that we must rationalize the denominator. All right, so remember when we deal with square roots, we have what are called conjugate pairs. All right, so just to kind of review that, a conjugate pair all right, so here we have the term, and over here we have the conjugate pair. So let's say we have 1 minus the square root of 3. So in order to find the conjugate pair, you only change the sign of your second term. So the conjugate pair for the term 1 plus square root of 3, excuse me, for the term 1 minus square root of 3 would be 1 plus square root of 3. So let's just say our term was negative 1 minus the square root of 3. Its conjugate pair would be negative 1 plus the square root of 3. Right? Only the sign for your second term changes. All right, so let's say we have 2 plus the square root of 3. Its conjugate pair would be 2 minus the square root of 3. All right. So in this case, we're going to multiply both the numerator and the denominator by the conjugate of the denominator. So the conjugate of the denominator is 1 plus the square root of 3. Right? So remember, whenever you multiply or anytime you divide anything by itself, this value is 1, right? 1 plus the square root of 3 divided by 1 plus the square root of 3, that should equal to 1. Anytime you multiply something by 1, you don't change the value. You simply change the way that your problem is expressed. All right? So from this point, we're going to multiply the numerators, and we're going to multiply the denominators. We're going to cancel, and we should have our final result. All right. So now there's a couple of formulas from algebra, and it should make the math on this a little bit easier. So I'm going to just kind of go through some of these formulas. So we have a plus b quantity square, right? And if you look close at the numerator, the square root of 3 plus 1, right, if we were to reverse the terms, is exactly the same as 1 plus the square root of 3. Okay. So in the numerator, we could use this formula, right? A plus b quantity squared, that equals to a squared plus 2ab plus b squared. Which means that if we have 1 plus the square root of 3 squared, right, I can substitute a for 1 and b for the square root of 3. So if we were to use this formula, a squared would be 1, right, because 1 squared is 1, plus 2 times a times b, so 2 times 1 is 1, 2 times square root of 3 is square root of 3, so that's 2 square root of 3. Plus, if we were to square the square root of 3, right, the square root and the square cancel, and we would have 3. And then we can combine like terms for 4 plus 2 square root of 3. I could also full method this thing out. All right. Now, I think the better algebra student would probably do it this way. Okay, but I'm just going to FOIL it out just to show you both methods. So this would be using the FOIL method. So 1 plus the square root of 3 times 1 plus the square root of 3. Right, I would multiply my first terms. 1 times 1 is 1. I would multiply my outermost terms. Right, 1 times square root of 3 is square root of 3. I would multiply my innermost terms. The square root of 3 times 1 is another square root of 3. I will multiply my last terms. Right, the square root of 3 times the square root of 3. That would give me the square root of 9. Right, and the square root of 9 is perfectly 3. Right, and then I will combine like terms. So 1 plus 3 is 4. 1 square root of 3 plus another square root of 3 gives me altogether 2 square roots of 3. Right, so that's our numerator. That's equal to 4 plus 2 square root of 3. In the denominator, we have a sum and difference of binomial, and there's a formula for that as well. All right, so I believe that would be a plus b times a minus b. That's equal to a squared minus b squared. So if we have 1 plus the square root of 3 times 1 minus the square root of 3, right, I can substitute a for 1. Right, so 1 squared is 1. I can substitute b for square root of 3 in the formula. So the square root of 3 squared, the square root and the square cancel. I'm going to bring down my minus, however. The square root and the square cancel, so I'm left with 3. So 1 minus 3 is negative 2. All right, so our denominator should be negative 2. All right, or I can FOIL it out. I'll actually FOIL that out. All right, so, okay, that's using the formula. We can FOIL that out, so 1 plus the square root of 3 times 1 minus the square root of 3. All right, we can multiply the first terms. All right, 1 times 1 is 1. We can multiply the outermost terms. One times, well, a positive times a negative is a negative. 1 times square root of 3 is the square root of 3. The square root of 3. We can multiply the innermost terms. We get a positive square root of 3. All right, we can multiply the last terms. A positive times a negative is a negative. The square root of 3 times the square root of 3 is the square root of 9. And the square root of 9 is perfectly 3. So we're left at 1 minus 3, which is negative 2. All right, so we have negative 2. Okay. Now lastly, we're going to simplify this. So remember the last time we talked about the divide by a monomial. And as I kind of mentioned, this is not really an algebra course, but it's sort of algebra heavy. So I'm just kind of reviewing some of those formulas from algebra. So the divide by a monomial states that a plus b over c, that's equal to a over c plus b over c. All right, we can rewrite each term having a denominator negative 2 So I'm going to write this as 4 over negative 2 plus 2 square root of 3 over negative 2. All right, now one thing you don't want to do in this case is just straight cancel. All right, because that violates our formula. All right, so notice I'm splitting it up first, and now I'm going to reduce. So 4 divided by negative 2 is negative 2. Right, a positive divided by a negative is a negative. And one node has crashed again. All right, so that's it's crashed again. Okay. I think I have to delete some of my tabs or something because I never erase these things, and I believe that's what's causing the problem. I have so many tabs open, I think that is the cause of the problem. And has it disappeared completely? Okay, I don't know what happened to the problem we were working on. I'm going to do the next one using the camera. Sorry about that, but I believe it was negative 2 minus, was it the square root of 3? Boy, I apologize for this. I believe it just crashed and deleted the entire page I was working on. All right, so that was the tangent of 105, I believe. So I believe in the top we had four plus 2 square root of 3, I believe. In the bottom we had 1 minus 3, which is a negative 2. And then we have 4 divided by negative 2 plus 2 square root of 3 divided by negative 2. I believe we should have negative 2 minus the square root of 3. Okay, so let's check this with the calculator. All right, so we had, just make sure that I'm in radian mode. Well, since I'm in degree, I'll use degree. So we had the tangent of 105 degrees, so that's the tangent of 105. The tangent of 105, which was negative 3.73. Next, I'm going to evaluate negative 2 minus the square root of 3. Right, and we have the exact value.